So let's imagine we've got a pole here that's supported on the side of a building. So there's a building over here. This is a wall. And this pole is supported here at a hinge on the building. And at the end of the pole, there is a sign hanging down here with a mass of 10 kilograms. And there's a cable going up from the pole up to the building, up toward the building and attaching on to the side of the building. Okay, like this. And we're going to look at the pole. We know that the pole is not rotating, it is stationary. So the object in question, the important object that we're looking at, is the pole. Okay, so what do we know? If it's not moving, we know the net force in the x direction is 0, the net force in the y direction is 0, the net torque acting on it is 0. Well, what forces do we have? Well, we've got the weight of the sign is pulling it down. And we know the sign has a mass of 10 kilograms, so that must be exerting a force of m times g, 10 times 9.8, or 98 newtons. The pole itself, let's assume, has a mass of 1 kilogram. So the pole itself has a weight of how much? Well, it's going to have a weight of the pole of 1 times 9.8, or 9.8 newtons. The weight of the sign, we know, acts at the very end of the pole. Where does the weight of the pole act? Now, here is where we can use what we just saw. The weight of an object, in terms of calculating its torque, we can assume acts at the center of mass of the object. Well, where is the center of mass of the pole? Let's imagine the pole is 2 meters long. It's a uniform pole, we'll assume. The center of mass would be right in the middle. So we will assume that the weight of the pole acts at the middle of the pole, straight down, with a magnitude of 9.80 newtons. Okay, great. What else? Well, we know the cable is applying a tension. So there is a tension this way. We don't know how much that is. Some tension T in this direction, up along the cable. But there's also some force acting on the pole from where it's attached to the wall at this hinge. But we really don't know what the direction is. It's held in place there, so it could have a force in any direction. Well, let's define our xy direction. So x will be positive away from the building, y will be positive in an upward direction. So the force acting here could be in any direction. Let's just break it down to begin with. So let's imagine that the hinge, this point, is applying a force on the pole in the x direction, or has an x component. We'll call it h sub x for the hinge force in the x direction. And it applies a force in the y direction. We'll call that h sub y. Okay, the hinge force in the y direction. Okay, great. There we go. Now, let's look at the net force. What do we have? What is the net force acting on the pole in the x direction? What forces do we have acting in the x direction horizontally? Well, obviously there's h sub x, so we'll have h sub x. And then what else? Well, not the weight of the pole, not the weight of the sign. The tension. The tension is going to have an x component. And we notice the tension is pulling this way in the negative x direction. The x component would be t cos 30 in the negative direction, so we'll have a minus t cos 30 degrees. Okay, anything else? Well, the hinges, the tension, the weight. Nope, that's it. What is the net force in the x direction? We know that is 0. Okay, what about the forces in the y direction? Well, again, we have a component of the hinge force, h sub y. We'll have a component of the tension. What's the y component in this case? Well, that's going to be t sine 30, but that's in the positive y direction. So we'll have plus t sine 30. But then we'll have the weights of the pole and the weight of the sign, both in the negative y direction. So we'll have minus 98.0 newtons minus 9.80 newtons. And what does all that all have to equal? That all has to equal 0. 0 net force in the y direction. Okay, what about the net torque? What torques are there? Well, before we can define the torques, we need to choose an origin. So where shall we choose our origin? Looking at this problem, let's think about what we thought last time or earlier. We can choose the origin anywhere we want, and if we choose it judiciously, we can make the problem simpler for ourselves. And how do we do that? By choosing the origin at the location where a force or forces act so that they are removed from the torque equation. Well, where could we do that? Well, how about right here? Why don't we define it at the hinge? Because we actually have two forces, well, the two components of one force, Hx and Hy, both acting at the hinge. If we choose our origin at that point, that would remove both of those forces, both of those components, from the torque equation. Okay, well, let's do that. So we'll define our origin at the hinge, and then what are the torques? Well, let's just go through one by one. And what do we have? We've got, let's see, torque due to Hx, 0. Torque due to Hy, 0. Torque due to T. Okay, remember, how do we find torque? Torque is equal to Rf sine theta. But then we also have to think, is it in the positive or negative direction? The tension. So what is R for the tension? Well, let's assume that it is attached to the pole 1.5 meters from the building. So R for the tension will be 1.5 meters. Times the force. What's the force? Well, we don't know what T is. So T times sine theta. Sine. Now, what is theta for the tension? Well, remember, how do we figure that out? We put R. What's R? R is the vector from the origin to the point where the force is applied, which is here. And here's the force, tension. We put them tail to tail. What's the angle between the force and R? It's this angle here. And what angle is that? Well, that will be 180 minus 30. In other words, 150 degrees. Sine 150 degrees. Be very, very careful about figuring out what those angles are. All right, that's the torque due to the tension. Now, is that going to be a positive or negative torque? Well, that torque, if you think R, F, that's positive. In other words, the tension is tending to rotate the pole in a counterclockwise direction. So that is a positive torque. All right, what about the weight of the sign? Not the sign. What about the weight of the pole? Sorry. What is R for the weight of the pole? Well, the force is at the center of the pole, and the pole is 2 meters long, so what is R? R is 1 meter. Times the force, which is 9.80 newtons, times sine, and what is the angle between R and F for the weight of the pole? R, F, 90 degrees. Sine, 90 degrees. And is that a positive or negative torque? Well, that is tending to rotate the stick in a clockwise direction, so that is a negative torque. Okay, one last force. The weight of the sign. What is R for the weight of the sign? 2 meters. Times the force, which is 98 newtons. Times sine. Theta, what's theta? Again, 90 degrees. And is that a positive or negative torque? That is tending to rotate the pole in a clockwise direction, so that is a negative torque. There we go. That's all of them. Hinges, tension, weight of the pole, weight of the sign, that's everything. All of that must equal 0. Well, there we go. Notice, what do we have? We've got one equation that only depends on T as an unknown. We could use this equation to solve for T. Then we could come back up here, stick it in here, solve for Hy. Put it in here and solve for Hx. I'll leave you to actually stick the numbers in, and I'll give you what the final result is. what we find is that the tension is 268 newtons that we got from the torque equation. From the forces in the y direction, from the forces in the x direction, we got 232 newtons. And from the forces in the y direction, we get Fy is negative 26.2 newtons. Why is that negative? What does that mean? Well, the positive x force means the wall is pushing on the pole. The pole is trying to swing back into the wall, and the wall has to push on the pole in the positive x direction. That makes sense. Why is this negative? Well, think about it like this. Here's the pole, and the tension is, the weight of the sign is pulling down on the pole this way. The tension is pulling up on the pole, but the weight of the sign is greater and pulling down, straight down, causing the pole to tend to rotate in a clockwise direction. To keep it from rotating in a clockwise direction, the wall has to push down on this end of the pole to keep it from rotating that way. That's why we end up with a force of Hy in the negative direction. It could be possible to balance these just so that the tension and the weight of the sign balance them so that you wouldn't have a vertical force acting on the pole. It would just kind of swing and just kind of rest against the wall like this without needing to be pushed up or down. Okay, very, very interesting result. Let's take a look at another problem.